Alright, this is 3.5, Part 1, notes about rational functions and their graphs. Okay, so what are rational functions? Rational functions are quotients of polynomial functions. Hopefully it'll clear up. Quotients of a polynomial function. So pretty much rational functions are when we have a letter in the denominator. That's a rational function. This means that rational functions can be expressed as px over qx, where p and q are polynomial functions, and q of x cannot be 0 because then it would be undefined, because we can't divide by 0. The domain of a rational function is a set of all real numbers except the x values that make the denominator 0, because we know again that if you divide by 0 it'll be undefined. So the first thing we're going to do is find the domain of each rational function. So we're trying to figure out what we could not plug in for x, because we don't want to make this denominator 0 because then it'll be undefined. The first thing though we'll have to do is factor out the top and bottom completely, and you'll see why. This top one's a difference of squares, so it can factor into x plus 5 and x minus 5. And then the bottom will be x minus 5. Can't factor the bottom. As you can see that when we factor, these will cancel out because x minus 5 divided by x minus 5 will be 1. And you're left with f of x equals x plus 5, which we know is a linear function. And if it's a linear function, a line, then we know the domain would be all real numbers, because a line goes left forever and it goes right forever. So the domain would be negative infinity to infinity, or all real numbers. And this part that canceled out is actually called a hole. There'll be a hole in your graph, like an open circle, at x equals 5. Now why is it at 5? Because that's what you will get, that's what will make this 0. If we plug in 5 for x, that'll be 5 minus 5, which is 0. So there's a hole in your graph at x equals 5 because it canceled out, and your domain is all real numbers. Okay, this next one we can factor out the bottom, can't factor the top, into x minus 5 and x plus 5. We can see that there's no holes because no factors canceled out. So now we look in the denominator, set these both equal to 0 to find out what they cannot be, or in other words what would make it undefined. This one would be x equals 5 because you add it over, x equals negative 5. So this domain is all reals except x cannot be plus or minus 5. Can't be 5, can't be negative 5. And what we'll have at these is called a vertical asymptote. I'm just going to put VA. You'll have a VA here at x equals 5 and x equals negative 5, and we'll get into what that looks like later. Over here we cannot factor the top or bottom because this is a plus sign. It's not difference of squares, it's sum of squares. We cannot factor this, but we can, so there's no holes, but we can set this denominator equal to 0 to figure out what our restrictions are. Move the 25 over by subtracting. Well, when we take the square root, it's going to be 5i, plus or minus 5i. Well, domain is only talking about real numbers, not imaginary numbers. So our domain is all reals. It could not be 5 or 5i or negative 5i. Well, that doesn't apply to the domain because domain just talks about all real numbers. So there are no vertical asymptotes here, no vertical asymptotes here, there's a hole here, no holes here. Alright, the next thing we're going to do is look at the parent function of a rational function, which is just 1 over x, the most basic one. They're going to give us some x values, and our job is to find the y values by plugging each one into the function. So this first one, when I plug in negative 4 to the denominator, I get negative 0.25. This one's going to be negative, or 1 over negative 3. That's negative 0.33. And I'm going to go ahead and fill this in quickly. If you need to pause and fill these in on your own, you can. Alright, you see at 0 that 1 divided by 0 is going to be undefined, so I'm going to put UND there, undefined. Again, here it'll be undefined. Put too many zeros there, sorry. 0.001. So those are all our y values. Again, we just plugged it into the function here. And now I'm going to graph these, but these x values are way too small to graph all of these points. So I'm just going to graph these from this table. And I want you to do the same. And as you can see, it kind of looks like on this side the points are decreasing. On this side they're increasing. And as it gets smaller and smaller, closer to 0 on here, you can see that our y values are going to go up, extremely up to like 1,000. So look like this. This is called a vertical asymptote, because it's approaching 0 but never touches it, and it's vertical because it either is going to go up or down without bound. Up and down without bound. That's a vertical asymptote. And on this side you can see that here's a vertical asymptote, and it's going to go down forever, not approaching 0. So this is what the parent graph looks like. This is what a rational function looks like. And why is there a VA at 0? Because if we were to plug 0 in, it's undefined. So it's never going to be able to touch 0 right here. It can approach it, but not touch it. Speaking of approaching, if we look at, this says when x approaches 0 from the left, the minus sign means from the left, plus means from the right. So as x, these are my x values, is approaching 0 from the left, so that's this way, from the left, approaching 0, it's asking what is f of x doing, what's y doing? Well, y is approaching what? It's going down, approaching negative infinity. We could also see that here. As x is approaching 0 from the left, it's going down, down, bigger to negative infinity. As 0 is approaching, or x approaching 0 from the right side, it looks like y is going up forever to infinity. And you could also tell that here. When it's going to the right to 0, it's getting bigger and bigger, our y values. Now, when you're talking about x values, when it says infinity, that just means right forever, not up or down like y. And as it's going to negative infinity, that means left forever. So as x is going left forever, in the direction left forever, what is our y doing? It's approaching what value? 0. And as x is going, as x is going right forever, y is approaching 0. As x is going left forever, sorry I did these backwards, it's still approaching 0. Alright. Next page, these are just some notations to talk about what I was just talking about. If it says x approaching a plus, that means x is approaching a from the right. This means from the left. As x approaches infinity, again, that means going right forever. This means going left forever. Alright, here's the definition of a vertical asymptote. The line x equals a is a vertical asymptote with a graph of a function f if f of x increases or decreasing without bound as x approaches a. So if it's going up or down without bound, it is a vertical asymptote. And now to find vertical asymptotes, that has to do with our domain, which is what we found on this page, the domain. So all we have to do on these three is find our domain. So again, make sure it's fully factored. I can factor out this bottom into x plus 1, x minus 1 using difference of squares. Nothing's going to cancel out, so I won't have any holes. And now look at the denominator. I set both of these equal to 0 to find out my domain and solve. This one's going to give me -1. This one's going to give me 1 when I solve. So I know that my domain is all reals except these two, and the reason that it's not, doesn't include these two, is because there's a VA, a vertical asymptote, at each one. So to find the vertical asymptote, pretty much just find your domain. Alright, I can see on this next one I can factor the bottom into x minus 1, x plus 1. And what I notice is that these x minus 1's will cancel. So what will I have left on top? I'll have 1 over x plus 1. So for my VA, vertical asymptote, I set this bottom equal to 0. X will be -1. So I have a VA at x equals -1. And I have a hole at x equals 1, where it canceled out. It'll be an open circle on my graph where x is 1. This last one, I cannot factor the bottom because it's not difference of squares, it's sum of squares. But I can set it equal to 0. And I can see that x is going to be plus or minus I. So in this one, I have no vertical asymptote. No vertical asymptote. Because again, your domain's talking about real numbers. Alright. Now let's talk about horizontal asymptotes. That's when it bottoms out at an x value, like a horizontal asymptote would look like this. If I had one, say, at 2, right here, at y equals 2, the graph would look something like this, like so it bottoms out. It's either going to go to negative infinity, talking about the left side, or positive infinity to the right side. Alright, and it all depends on, horizontal asymptotes are determined by looking at your exponents. So you're either going to have equal powers in your top and bottom, your numerator and denominator, or you're going to be bottom heavy, which means highest powers in the bottom, or you're going to be top heavy, highest power in the top. What I mean by powers are the exponents of your variables. So for example, highest exponent on top is 2, highest exponent on bottom is 2, so they are equally powered. There's x squared on top, x squared on bottom. So if they have equal powers, you just take their coefficients and divide them. So 9 divided by 3 is 3. So we have a horizontal asymptote at y equals 3. Because y equals 3 is a horizontal line, where x equals something is a vertical line. Now this one, the highest power of the top is 1, the highest power of the bottom is 2, so it's bottom heavy. So when it's bottom heavy, think of 0. And I drew this 0 funny looking on purpose. I drew it to look bottom heavy. If it's bottom heavy, you'll have a horizontal asymptote at y equals 0. Alright, this one it's top heavy, you can see, because the highest exponent's up here, so this has no horizontal asymptote. So go back up here. Equal powers, divide. You divide the leading coefficients. Bottom heavy, y equals 0. It's at y equals 0. Top heavy, none. No HA. And here is what two horizontal asymptotes would look like. Here you can tell the horizontal asymptote is at 0. Here you can tell it is at 0 as well. Alright, we're going to skip this using transformations and come back to that. Let's skip straight to graphing rational functions. You can mark out this symmetry. We are starting with finding the y-intercepts. That's when we set x to 0. X-intercepts when we set y to 0. Vertical asymptotes, which we talked about setting the denominator equal to 0. And then horizontal asymptotes by looking at the powers. Alright, starting with y-intercepts. That's when you set x to 0. Y-intercept, set x to 0. So if I set x to 0, I can pretty much just cover these up because they're both going to disappear. And I'll get negative 3 divided by negative 2, which is a positive 1.5. Y-intercept, or x-intercept, I set y to 0. Well, the only thing that's going to make this 0 is when the top is 0. Right? Because we know if the bottom's 0, it's going to be undefined. So we're just looking for where this top, what we'd have to plug in for x to make this top 0. So we set it equal to 0, solve, we'll get x equals 1. So our y-intercept is 1, 0. For the vertical asymptote, we're just looking, well, first let's factor. We get 3 x minus 1 over x minus 2. The vertical asymptote is going to come when we set the denominator equal to 0. You can see easily we'll have a VA at x equals 2, because if we plug 2 in, 2 minus 2 is 0. For the horizontal asymptote, you can see they're evenly powered, because they both have a highest exponent of 1. So when we divide 3 divided by 1, we'll get a HA at y equals 3. Now we're ready to graph. I'm going to graph these 2 points first. I'm going to draw dashed lines where my VA would be and a dashed line where my HA would be. Alright, well, you know there's going to be something on each side of the vertical asymptote and the horizontal asymptote. Well, we have 2 dots, and that's just about all you need for this side, because you know it's going to approach this asymptote but not hit it. You know this one's going to approach this asymptote but not hit it. So that's part of our graph. The other part, we're going to have to choose 2 x values on the side of this asymptote. So I'm going to do 3 and 4, because they're right there, to figure out what's going on the other side. So here's what I want you to do. Plug in this function into y equals. So hit y equals button. Clear that out. Put parentheses 3x, that's the original, minus 3 divided by x minus 2. Hit graph. And we can kind of see what it looks like already. But this table, I want to use it to figure out exactly where 3 and 4, what the y value is for them. So at 3 it says 6. So I can't graph that one, but at 4 it says 4.5. I can do that one. And if 3 is going to be 6, so it's up here, I can tell what my graph is going to be doing. It's going to be approaching this asymptote, approaching this one, and my graph confirms that right here. And we can see it says error at 2, because that's where the vertical asymptote is, at 2. Alright, let's try another one. Start with the y-intercept, set x to 0. So if we set x to 0, I'll get a 0 on top. Doesn't matter what I get on bottom, it'll be 0. For my x-intercept, just set the top to 0, and you can see that's going to be 0 as well. For my VA, I can't factor it, so I just set the bottom equal to 0. I'll have a VA at y equals 2, x equals 2. And these are evenly matched, so there's going to be an HA at 4, at y equals 4. Now I can graph 0, 0, and I can put dotted lines where my HA and VA are. But I'm going to have to use my table, my graph, to figure out some values. So I'm going to circle the ones I want to plug in. I definitely want to do 1, maybe -1 if I need it, and 3 and 4. So go ahead and plug this in. Oops. Alright, now I'm going to go over to my table, figure out what's going on at 1. Alright, at 1 the value is -4. Well, that's all I really need, because I already had 0, 0 points. So I'm going to draw my graph like this, come up to here. You can see that's what the graph is doing as well. Alright, and then on this side, 3 and 4, let's see what's going on there. We got 12, definitely can't graph that. 4 is at 8, can't do that one. So I'm not going to draw this piece because it's just way on up there. There we go. Alright, next one. So on this one, the y-intercept, set x to 0, you'll get 0, 0. X-intercept, same thing. HA at, let me do VA first. VA at x equals 2 and x equals -2. HA at y equals 0. So I know this one looks weird because you have a HA at y equals 0, but then you have a point at 0, 0. But the horizontal asymptote and vertical asymptote doesn't necessarily apply to each piece. Now, the ones we've only looked at only have 2 pieces. This one actually has 3 pieces. 3 pieces, and the reason why is because the highest exponent is 2, unlike the other 2 we did where it was 1. So, go ahead and draw your VAs first, and HA. See, this one has 2 VAs, like the other ones only had 1. So you have 3 different pieces on this one. So I'll start by putting this in. And then go into my table. Alright, first I want to get what's going on at -3 and -4 on this side of the asymptote. So at -3 it's at -1.2. At -4 it's at -0.667. So this is what this side's going to look like. Can't touch this asymptote nor this one. Then I want to figure out what's going on at -1 and 1. So at -1 I'm at 0.67. At 1 I'm at -0.67. So I know these are going to connect. This one's going to approach this asymptote. This one's going to go up here. So even though it crossed through 0, 0, this point right here has the horizontal asymptote. The middle piece doesn't necessarily apply. Now I'm figuring out what's going on at 3 and 4. So at 1.2, at 4 it's at 0.67. And there's my graph to confirm what it's supposed to look like.